So now let's have a closer look into how do we communicate in the World Wide Web. We'll discuss HTTP, WebSocket, WebRTC. Remember the three scenarios: classical web pages, or something that tries to push something to you, or multimedia communication. We'll see where and how we use which of these protocols and techniques. So first of all, let's start with the classical scenario. Classical scenario, that means standard communication. That is what the web was made for. Mosaic first browsers, basically you have your client with whatever browser on top of it, Firefox, Chrome, Safari, Opera, Edge, whatever. And then, yes, they may have several plugins and several fancy features, but in the end, the classical browsers request content. Okay? And then we need a server. Yeah, then we have servers, web servers, Nginx, Apache, Cloudflare, Lightspeed, whatever, Microsoft Internet Information Server. So different servers, and then they will do something and response. We'll have a closer look how this looks like. So classical client server scenario, very standard. Additional modules and additional helpers are there, and we have certain security issues there. And today we can say actually browsers basically are something like a mini operating system running within the operating system of the host machine. So Google and with Chrome push this vision really far, and there's a big advantage because actually if you program your application using HTML5, cascading style sheets, and JavaScript, this results in platform-independent applications running on all systems having a browser. And maybe you noticed that all the companies go away from dedicated applications for special operating systems towards applications running in a browser. The whole Office suite of Microsoft, Google, etc. runs in a browser, and you do not need a Windows any longer for Microsoft Office. You can run it on whatever machine as long as you have a browser. There might be some problems here and there, but that's the basic idea. There are tens of thousands of pure browser games, so even for gaming, you do not need the special features of operating systems. So that means the games run in the browser. Yes, for high performance games, etc., high frame rates, high resolution, etc., you need special features of high performance graphic adapters, etc. Yes, so there are reasons why sometimes you need native operating systems, etc., for your games. But for a huge amount of games, you don't need this anymore. You can just run them in the browser. This also helps you if you have a browser on mobile devices. So why development for mobile devices? Develop using HTML5, cascading style sheets, JavaScript. So the content is described in HTML. The look basically is described in cascading style sheets. And the dynamic behavior is described using JavaScript. This triple basically defines how your web page looks like. But this course is not about web page programming. There you find many other courses also on the web. We will have a closer look into the protocols. So basically what's going on here, because this is all about communication. So HTTP, the Hypertext Transfer Protocol. As the name says, it's a protocol to transfer hypertext. Whoa, big surprise. So that's the standard protocol we use between the web server and a web client. So typically in most of the cases, if you load a web page, use HTTP. There might be some other case, but HTTP, that's the standard. And typically, the server waits behind port 80. Port 80, well-known port, and you use TCP because you need reliable transport. So that's the idea. And the idea is also, please make it very simple. And remember, email. Classical email, you can read everything. Classical DNS, you can read everything. So it's text-based. It's a very simple ASCII text-based protocol. So HTTP, again, we have an ASCII protocol. We can read it, the classical version. So the client requests data and the server always responds. That's the idea. How to identify what we want to read? Well, that's our URL. And there's another idea besides, well, let's keep it very simple, text-based. It is stateless. So the classical HTTP protocol is stateless. What does it mean? You send a request and you have to provide all information that is required to process the request inside the request. So the server gets a request, and we will see examples for this, and this request contains all the required information. Then the server goes through the request, processes the request, and answers. The server does not store any additional information. So that's the idea. No history on the server. So that's the idea of being stateless. So there are pros and cons, we'll discuss this, but that's the basic idea. So you asked 1,000 times about a certain resource, the server doesn't know it. The server will deliver again and again and again the same resource depending on the URL. So you have to specify of the whole context for every request. And we will see this is quite verbose. So you cannot tell the server, give me the next picture. Which next picture? There is no history in the server. You always have to say, okay, now give me picture number 85. And the next time you have to say, now give me picture number 86. You cannot say, well, the next picture after 85. Hell, do the calculations on your own. The server doesn't know anything. That's the key idea. Why? Well, because if you store state, things become complex. So you have to maintain state. If one of the parties crashes, then maybe they have inconsistent views of states. Plus, if you have state, you can way easier attack a server. So you create more and more state on the server until the server runs out of memory. So this can be a big problem. That's one of the reasons why I say, please, no state. Don't store any state. That's the idea. Maybe you know this from programming. So HTTP basically provides an API that complies with the REST architecture, representational state transfer. That means it's stateless, it's cacheable, it's layered, which results in better performance, scalability. It's way simpler. You can way easier modify it, portable, reliable, etc. So that's the idea. So to keep things simple. I wrote here prior to HTTP 2, and we will see there is some state stored somewhere, and there are some reasons why today we are not completely stateless anymore. We can discuss this. But let's go back to the basic protocol. How does it look like? So first of all, an HTTP request. It's all text-based. That means you really have a command that says GET blank HTTP colon, etc., etc. So it's written, it's ASCII based. So first you have a command, and after the command, for example, get, there are some others we'll see, then a protocol follows. The protocol, the most well-known, is HTTP. But there are, for historic reasons, also some others, like FTP, for example. That's just another protocol. We will see there's also WS, WebSockets. There are some other protocols, go for some more historical ones, etc. But HTTP, that's the classical one. So we tell the protocol. After that, we tell the server domain name. You know this from DNS. Okay, we have a name, we know DNS. DNS, we will use DNS to map this to an address. Okay, and after the name of the server, there might be a port. If you skip this, then we assume automatically 80. If it's not encrypted, then we assume 80. So that's a well-known port where the web server listens. And after that, we specify the path to a resource. That's exactly what you know from file systems. and the file name. So that's the basic idea. So it's very simple. Protocol, the server name, a path name, and the file. And then we have several commands, and typically what you use is get. That's how you load the resource. So that's the idea. Yeah, you can also, if the server allows this, store something. That's the idea. You can delete, etc. But get, that's typically what you use. That's the idea. And then there are some more. So you want to get a resource, then you issue this command in HTTP. The protocol will transfer it. So GET, etc. So yes, very verbose, but that's the idea. Very simple, very easy to debug, very easy to read. That was the idea. Remember, email and DNS. So how does it look like in some more detail? Well, this is how then the HTTP packet looks like. This is where we have our method, get for example. Then we have a space, blank space, then URL, etc. space, and then some version. We'll see some examples. That's the idea. So you must have this request line, otherwise what should the server do? And then we have some optional lines, like certain header lines, like a body. This depends on the method. So if it's get or if it's put, so if you put something, you need some content to put on the server. So that's the idea. So request line, mandatory, header lines, optional. Use for further information. So that's the idea. So you can say, for example, well, so get this and that, and then you can say server, accepted language, user agent, etc. Or you can skip this. You can tell the server which browser you use. You can fake this. You can tell the language, whatever you like. So the server should be able to process it also. I mean, even without this information. So that's the idea. But if you fill in, for example, an online form, then it makes absolutely sense to transmit the data. If you fill this in the form and then you send the data with post, then you use the post method and send data to the server. So that's the idea. So it's all clear text. So that's the idea. It's not compressed, it's not encrypted. So request lines, header lines, and then maybe a body. It depends if you transmit data. Now, how does it look like? Just some examples. So you request this, and then you will get something. Okay. Oops. What is this? It tells you status line HTTP 11. Okay. 200. Okay. What does it mean? You send your request, and again, as ASCII text, the server will answer. And it really sends this as text, including space, etc. All this, giving you a code back, telling you in this case everything is okay. It explicitly writes 200 space okay. Closes the connection, will come back to this, sends some header lines, etc. And the header lines, you see there's something we know. Let's look similar to something we have with MIME. In email tells you a text will follow, and the subtype of the text is in HTML. It also tells you the date. It tells you when the document was last modified, etc. So each time you request this resource, the server will tell you, oh, today is August the 6th, 1998, etc. And it's 12 o'clock, etc. Greenwich Mean Time, etc. Blah, blah. And after this, the data will follow. This is very verbose. So you get the time and the date each time you ask. So is this interesting for you? Just think of, you have a mobile device, battery driven, you don't have that good connectivity over the air, or you pay for each bit or byte, for example. depending on, well, if you do not have a flat rate. So this is something you have to pay. If you pay per byte, this all contributes to the data you use for your mobile phone connection, for example. Okay, but that's the way it is for this classical HTTP. So the response looks pretty similar to the request. You have this status line now. That's the response with a status code telling you everything is okay, or this very prominent 404, well, not found, resource not found if you ask for something that's not there. And so you have different groups of status messages for information, for something successful, or for something with an error, server error or client error, for example. You ask for something I do not have, then it's a client error, or there was a server error, for example, if the server can answer at all. So again, status line that is needed, and then there might be several header field names, and then there might be data. So if you find the resource, then we will have data in it. So that's the idea. Okay, so that was more the theory. How does it look like in reality? We load a web page. So you click on a link. You do this hundreds of times every day. You click on the link in your browser, and then what happens? So now we do not mention UDP, TCP, layer 4 stuff, only on the application layer. First of all, we have to ask DNS for the IP address of the server, because all you have in your URL is the name of the host. So we need the IP address because HTTP wants to start a TCP connection. TCP needs for the socket an IP address. Okay, so DNS. So you go to the DNS server, and then DNS server comes back. We learned how to do this recursive, iteratively, etc. Comes back with an answer. So that's the idea. Then we know this answer will tell you here the IP address of the web server. And then we can start establishing a TCP connection to the well-known port 80. Well, unless you write another port in it. So that's the idea. And over this TCP connection, so we do the three-way handshake. We'll have a closer look later, TCP and new developments. You send your command. I want to have this whatever file. Then the browser transmits this, server answers, sends back this file, and terminates the connection. That's the basic idea. We will see how caching improves this, etc., to reduce delay and so on. But this is the basic way how this is done. Okay, is this theory from many years ago, HTTP? Well, let's have a look. So let's access this web page of our department, Math Informatics. To do so, please go ahead, install Wireshark. Install Wireshark, dig into documentation, at least that you know what's going on. Start recording what's going on your network interface, and then click, for example, on the above link. Oh, you will see many, many, many packets. You have to stop recording in Wireshark and then have a closer look. After some search, you will find a DNS lookup. And this is an example on how this is typically represented in Wireshark. Very brief intro. That's the packet number 22. There's some time after starting. And the more important is, okay, that's the computer, in this case, my computer, private IP address, coming back to this, asking a DNS server. So please, you see what's going on? It's DNS. Please here tell me resource record A. Remember, that's the address here. So address. Please tell me the address of www.mi.fu-berlin.de. After a while, so I filtered out all the packets in between. Please learn how to use filters. The system that the DNS server will answer, you see here, that's exactly the answer. So we see here the source and we see here the destination. The server will then answer, it's also DNS, sure. Well, it's the response address. Well, for this computer, it's this IP address. Okay, 160, 45, 117, 199. Okay, so that's fine. And after this, we can then set up the connection. You know from the bachelor courses what TCP does? Maybe you remember a three-way handshake. Three-way, that means, well, first, my computer, you see, that's the same computer from above, that's my computer here, sets up a connection now to the web server. That's exactly the address I got via DNS. Now we use TCP as protocol. And what do we do? Okay, we set up a connection to port 80. Remember, bachelor course, the operating system will give you a port number. That's a port number on my side. So what we do actually is we create the socket pair. The socket pair on my side, we have the source IP address, that's my side, and my source port, now that's the 5625. And we try to set up a connection to our server. That's our web server. That's the destination IP address. That's exactly our IP address from above. And we go to port 80. So you see, and we'll come back to all these sequence number, window sizes, etc., etc., when we come back to TCP. But what you should know from bachelor is, okay, that's the first step. First, we send a so-called SYN packet with a SYN flag set. Then the server answers. Step number 2, you see, it answers with a SYN ACK. And then step number 3, we answer with an ACK. So this is the pure and classical three-way handshake. And this takes time, which is a problem. This takes time. Imagine with the classical HTTP protocol, we have to set up a connection for each and every request. Because after this connection, well, after this transmitting the content, we tear down the connection again. So three-way handshake, and then we have a connection, yippee, and then we can transmit, now it's HTTP, exactly get the index switch. So get /HTTP/1.1. So very classical. You cannot do this with all the servers. We'll come back to this. So many servers today, they will not allow this because they accept only HTTPS, so encrypted transfer. They accept only newer protocols, etc. But here, for demonstration purpose, I can show you this. So now we send, well, please get me this. How does it look like? So that's exactly what is sent in this case. Oh, this looks a bit more complicated. It's still this very old protocol on purpose. So you see, okay, very old protocol 1.1. Today we can use 3, but okay. And we see, okay, now please go to this web server, etc. and many more things. So this is the important part. That is mandatory. But then there are many optional things like, okay, what is the user agent? At least what does the system tell, etc., etc., etc. You see here. And then we see, similar to this MIME things, you see, okay, we accept HTML, but we also accept other formats and so on and so on. We accept, for example, encoding zipped content to compress the content. We accept different languages and so on. So many more things. So that's only a part of the packet, actually. So what is the answer then? Okay, after this, the server answers and says, okay, everything fine. So we asked for this, and at least the server tells us everything is fine. And as you saw on some slides before, it tells me it's Saturday, this is the time, etc., etc. So we'll get every time we get the time. Okay, how interesting. And then it tells, okay, what type of server this is, and so on. We see something called e-tag. I will come back to this when we discuss cookies later. And then tells us there's certain encoding, content types, etc., etc. And after this, we are not interested in the headers. Yeah, that's the interesting part. We finally see, okay, yeah, here it starts HTML, etc., title. That's the department for math and computer science. And as you may notice, that's the German page. Okay, so that's the idea. We send the request, we get the response, including the content and a lot more information. We'll not go into all the details of all these lines, but at least into some, like the e-tag. So, okay, problem solved for scenario 1, our classical client-server pull scheme. Yes, it's verbose. Yes, they talk a lot. Yes, we need many requests for a whole web page, but HTTP, even the old versions 1.1, solves this problem. But we had other scenarios. What happens if the web server wants to push content to the client? This doesn't work with a classical client-server pull. HTTP is a classical request-response protocol. So, if you want to renew your page, you have to click and click and click and click in your browser. You have to pull explicitly. Or you can fake this pushing by a browser that pulls every 10 seconds. This has been done also. But this is really a large overhead. That's not a good idea. We'll see there's a solution for it. It's called WebSockets. But even more, what if we want to enable communication between browsers? HTTP is a classical client-server protocol. So do you want to have a server also integrated in your browser? That's one way of doing it. So you remember the peer-to-peer paradigm where I said, okay, all the nodes have a client and a server integrated, and they can act as client and a server to enable peer-to-peer communication. But you really want to integrate a web server? Oh, that's too complicated. And the solution here is WebRTC. So WebRTC allows this direct communication between browsers. So first of all, WebSockets. What does it mean? Now that's a bit newer, and WebSockets, they allow efficient full duplex communication between web servers and clients without the need for HTTP. So maybe you can use HTTP for a starter, but then we can use something else, as you'll see. So WebSocket URLs, they can look a bit different, and you see now, okay, we don't have to go for HTTP, but there's also WebSocket and there's also a secure version. Just an example. So basically, it works in a way that with WebSockets, you can still use those ports, 80, that's a classical well-known port, 443, that's for the secured version. I will come back to the secured versions of the protocols when we discuss security in a separate chapter. So TLS and HTTPS and all these protocols. And all the requests by the client, they look like HTTP GET requests, but they have a so-called upgrade offer integrated. So you send a normal HTTP GET request with an extra line telling the server, I want to have an upgrading HTTP into a TCP socket. And then the server replies with, yeah, let's switch protocols. And after that, you have enabled a classical socket communication, TCP communication between the client and a server. And this is bidirectional. And as with all the TCP connections, you can simply send some data over it. Now also from the server to the client without the need of the client to pull all the time. So this is how you can enable pushing content to a client. So basically, you use the mechanisms of HTTP to create a TCP connection that you then can use for arbitrary communication. And this is how you can then integrate something like tweets on web pages. What if you want to do even more? Even more, that's multimedia communication, WebRTC. So that's a way of implementing real-time communication now in web browsers. So without the need of a web server in your browser. So you can act as server and client. How does it work? So we bring this idea, this peer-to-peer idea into browsers. Okay? So there IETF worked together with the World Wide Web Consortium. So IETF is more for defining the protocols, and W3C defines the APIs. So there you will also find some more information about WebRTC. The idea there is that you integrate certain functions to establish multimedia communication. So plus maybe a data channel. So audio, video, and data. And that really became quite popular over the last few years, together with the pandemic situation we had in many, many places. So we needed video conferencing systems, at least with low number of participants. We can discuss this. Why? Only a low number of participants. So but quite popular. So there are then functions like get user media, where you can say, okay, I want to have audio, the microphone, and video, the camera of your laptop, for example, of your PC. And you can enable start your peer connection, so to another computer. And so for the audio and video streams. And additionally, you can set up a bidirectional data channel, so for peer-to-peer data communication, using a protocol we will also discuss, SCTP. So the Stream Control Transmission Protocol, SCTP, a protocol heavily used, was the starting point in the infrastructure networks for mobile communication systems, with certain advantages over the classical TCP. We will come back in a later chapter when we discuss different new layer 4 protocols. So we can now enable real-time communication, and sure, you can have a closer look into this. It's just the rough idea. So first of all, you need, and this is outside WebRTC, a way of signaling up here. Where's the server? How do I find my peer? What kind of coding, etc. do I use? All these things. So there's a lot of signaling involved here, and they're between the servers, etc. And what WebRTC then solves is, if you are on the browser and you have your information how things work, then you can set up your data path and your multimedia path. So there is some additional work needed. For example, if you have systems like Big Blue Button or the other video conferencing systems, how do I find my peer? How do you start this and all these things? So there are some more servers needed for this. But that's out of the scope how you do all this signaling. So WebRTC solves the problem of browser-to-browser multimedia communication. So that's the idea, without going into all the details. But you see, for these special scenarios, like, oh, I want to have a push service, or I want to have real-time multimedia communication, we need some add-ons. And WebRTC is the newest add-on we have. So if you're interested in this, please follow the links to see how it then works in some more details. For now and here, let's focus on these protocols. So first, the classical protocol, HTTP 1.1. So what are the advantages, disadvantages of this classical protocol? And this is important to know, because this will then motivate the newer versions. please do go ahead, install Wireshark and check the traffic flow. Click on the URL, learn how this works, learn the basic filtering. It's important how you identify a traffic stream, and especially how Wireshark represents different layers. That is not always easy because sometimes it differs from the standard and how this is represented in Wireshark, but you will find all the layers, IP layers and layer 4, the TCP and HTTP, etc. So that's of great help. So if you do this, and even if you know how to filter and how to identify a traffic stream, why are you quite often frustrated? Why do you typically see nothing from the content? You don't even see the requests and responses. So now you have Wireshark, you want to look into something, but you don't see anything. You only see something like TLS here, TLS there. So why is this the case? We'll come back to this. Then think back for different application scenarios. The classical client-server idea, well, requesting content of web pages. But then what happens if you need push? What are typical applications then for the WebSockets? And then we had the newest idea around several years old, WebRTC, now real-time communications. At least WebRTC solves the problems browser-to-browser communications with certain APIs. Still, you have to know where the participants, who's participating, all these things. This is handled outside. But still, what could be problems using this peer-to-peer scheme for video conferencing if you have many participants? When we talk about thousands, 10,000 participants, what happens with this peer-to-peer idea if many participants want to talk to each other, etc.? Maybe you can even think of how is this solved? Because this sounds like WebRTC is maybe not the best idea. We will discuss this.